Two or three items already. We've had the famous L'Hopital, a fancy way to find limits when you've got the right form and when the limits of the derivatives exist, blah blah blah. We had a nice way of approximating numbers like this with nothing but hands and a little pride and noodle power. That was nice. We had a way of finding the degree 1 sketch of a graph, meaning the uphill downhill business, just by studying the first derivative, with the small but important point that a first derivative is positive when the function is going uphill, the first derivative is negative when the function is going downhill. That led to some very nice results. We get a rough sketch of the graph, and what we got to do today is add to our list of things that we can use derivatives for. Today we're doing what we call here a degree 2 sketch of the graph. What it is just an improvement, a substantial improvement over the previous version of the graphs for just random functions where we can study their derivatives. Okay, that's what we got to do today. The key idea, the key idea, what it is just the key idea from the last lecture, and we've just sort of nourished it a little bit to make it grow up and become something a little bigger than it was before. Let me tell you, the key idea from the last lecture was that if f of x was greater than 0, f prime of x was greater than 0 at some point c, we knew exactly what that meant. That meant that the tangent slope, whatever it may be, was going uphill. And if that's your tangent slope, this is f prime of c, the slope for it is f prime of c, then the function had to mimic it, so the function would have to go something like this. Maybe it has to mimic that line really closely, so long as you zoom in enough, right? So what that meant was that f prime of c greater than 0, what that meant was that f of x was going uphill near this point. But we don't really say uphill. We say the fancy way to say it is that f of x is increasing near the point x equals c. Okay, sometimes I forget to say this, but it's near x equals c. You have to zoom in enough to make that happen. That's the idea from last time, and that's the idea that we gotta nourish today and milk, sort of, and take it 2 or 3 levels higher. That's precisely the idea. Now to do that, let's study it. Let's sort of take the abstract idea here from it. Whenever f prime of blah is positive, that means that the original blah was increasing. You could change that into something else. If r prime is positive, then the original r is increasing. And there's nothing special about f and f prime or r and r prime. You could apply this concept to almost anything that you can think about with derivatives. If g prime is positive, then the original g is increasing. But something interesting happens when you apply exactly this concept to something that's already a derivative. That's this is exactly the idea from last time. Something interesting happens when you apply it to f double prime. If f double prime is positive, what does that imply? Well, it says something about the one without one of those primes. It says something about f prime. It says that f prime must be increasing. This isn't a new idea. This is exactly the same idea from before, just taken up a notch or two. Okay. If it helps, you rewind this and see that there's nothing different. Our g here, I had an example there. Pretend g is equal to f prime of x. Then this statement is exactly the same as the statement with g of x from just a couple of slides ago. Clear? But again, the idea is much bigger. We can generalize it. Look, if f triple prime is greater than 0, that means that the f double prime was increasing near c. So it was the one before that prime, the thing that you took the derivative of, that's increasing. If this is the third derivative, that means you took the derivative of the second derivative, so that's the one that's increasing. Again, if you take the fourth derivative and that's positive, that means that the function with the third derivative, that one must have been increasing, etc., etc. But we're not interested in all of them. The one that we are most interested in is exactly this one right here. This is the one that we got to focus all our attention on today. If f double prime is positive, that implies that first prime is increasing. In fact, I say that for the next 5 minutes, we do nothing but focus all our attention on on exactly this statement right here. Focus all our attention on trying to understand what in the world does that mean. That right there, that's what we got to focus on. Okay, have I made my point? This is it right here. Exactly what does it mean when we say f prime of x is increasing? Let's try to take that and break it down. F prime is increasing. F prime is a little machine that generates tangent slopes, right? If somebody says to you, hey, the tangent slopes are increasing, what does that mean? Can we make sense of that? If we could, we'd be in good shape for today. I mean, really, the lesson boils down to that idea right there. What does it mean when the tangent slopes are increasing? Well, let me think. Think. What does it mean when f prime is increasing? Salute. This is such a no-no to have dead air in videos. Alright. That's what we got to focus on. What does it mean for f prime to be increasing? For tangent slopes to be increasing? Well, we really have no business studying tangent slopes anything if we can't even handle just regular old slopes. So I thought it'd be instructive to start off with something like this. What does it mean to have a bunch of regular old slopes like m? We'll call them, say, m. Whoa, take it easy. Excuse me. Say m is equal to, let's write a few m's that are increasing. M is equal to 1. M is equal to 2. M is equal to 3. M is equal to 5. These are increasing, right? What does it mean to have a bunch of slopes that are increasing? Let's try to make sense of that. M is equal to, if this one is, let me see. M is equal to 1, that looks more or less like this. The slope is 1. M is equal to 2 would be rise over run. It runs 1 and rises 2, so it would be more like this. M is equal to 3, it would rise 1 and run 3. M is equal to 5, well, that one would run 5, run 1, rise 5. This is what it means to have a bunch of slopes that are increasing. And you could even do it differently. You could say, well, what if it was different increasing? Well, let me do that in just a second. Here's another. Let's do the same example one more time. This time let's say m is equal to negative 3, m is equal to negative 2, m is equal to negative 1, m is equal to 0, m is equal to 1. Are these slopes increasing? We always move from left to right. As you move from left to right, negative 3, negative 2, negative 1, 0, 1, that's increasing. So the slopes are increasing. And it's instructive to draw little pictures of these and see what does it mean for them to be increasing. Negative 3, rise over run. So you run 1 and you go down 3. So it would look more or less like this. Rise 1, go down 3. This one is run 1 and go down 2. So it's still like that. You go over 1, down 2. This one, 1, 1, 1 to 1. 1 over, 1 down. This one is flat. This one is starting to creep up. That's what it means to have a bunch of slopes increasing. This is just another example of a bunch of slopes that are increasing. What's interesting is once you're good with just regular slopes that are increasing, you can add this extra ingredient, increasing tangent slopes. Increasing tangent slopes. See, these are just regular slopes. These are tangent slopes. If I have a bunch of them that are increasing, let me just draw some typical ones that are increasing. Let me give you some f prime of, say f prime of 0 is equal to 1, f prime of 1 is equal to, no, I'll just start off with 0, 1, f prime of 2 is equal to 4, f prime of 3 is equal to 10, whatever. I'm just making some random numbers. These are my slopes. My slopes are 0, 1, 4, 3. I just have an increasing sequence of slopes, but they're not just regular slopes, they're tangent slopes. So they have to follow a certain curve and be tangent to that curve as you move. So what could that possibly look like? Well, it's almost the same as before, but now they have to make sense together. At 0, this is the slope 0. At 1, your slope is more or less like this. At 2, it's more like this. At 3, it's more like this. And so if these are all part of the same curve, they're all tangent to the same curve, they tell you something about the curve. The curve must have this sort of shape. Well, now we're getting somewhere, because this sort of shape is famous. It must have this sort of shape, and that, my friends, that's called concavity. This is telling you the concavity. This is called concave up, meaning like this. It holds water. That's concave up. This is really, really fancy. A fancy way to say that the function is concave up is just a different way to say it is that your first derivatives are increasing. Isn't that nice? It's a really nice characterization of the curves. It's concave up if the first derivative is increasing. The function doesn't have to be increasing for that to happen. You could also have concave down and decreasing. Watch this. Suppose we take these ones over here, but suppose that, let me make a copy of this. I'm going to clone this one, and suppose I change it a little bit. I go, you know what, instead of doing that, I'm going to do not increasing slopes, but increasing tangent slopes, right? So instead of these just being regular f's, they're regular slopes. They're f prime of something, f prime of 0, they're f prime of 1, f prime of 2. They're all f primes. So that means they have to follow the same line. So this one's maybe at 0, this one's maybe, whoa, what happened there? Whatever. Let's delete this one. This one's maybe at 1, this one's maybe, they all have to be part of the same curve. And so what you get is, again, this very nice shape. Bam, just like that. They have to follow the same curve being tangent to it. Of course, this assumes that the original function is nice and continuous, and its derivative is continuous, and the second derivative is continuous, all that stuff. So the ideal condition. But under those cases, look at how nice you get. You get something that, again, the same situation. If your tangent slopes are increasing, you're concave up again. You may have to think about it a little bit more or do more examples, but you can almost rack this one. This result, you can put it in a little box and say, hey, this has to be a general concept here. If f double prime of c is positive, okay, it's bigger than 0, that means that f prime of x is increasing. That means your derivatives are increasing near that point c. Maybe you have to zoom in a lot, but if you zoom in enough, your f prime is increasing around that neighborhood of c, which means that f, the original f of x, is concave up. Nice, huh? Concave up. By just checking the second derivative. Oh, but wait, there's more. Let's try a one where it's decreasing, yeah? What if you have a decreasing sequence of slopes? Well, a decreasing sequence of slopes, well, first of all, let's just write down some numbers that are decreasing. M is equal to, say, 1, m is equal to 0, m is equal to -1, m is equal to -2. This is a sequence that's decreasing as you move from left to right. Right? Can you pause this? Let's just draw some sample random decreasing slopes and see what they look like. What does that shape tells us? The slope is 1, well, that would be something like this. Slope is 0, that would be something like this. Slope is -1, that would be something like that. Slope is -2, that would be something like that. But wait, there's more. Something interesting happens when you turn those not into just any old Joe slope, but into tangent slopes of the same function. Whoa. Now we got ourselves something, because, let's do it again. Now if f prime of something, f prime of 1 is equal to -1, f prime of 0 was equal to, wait, f prime of 1, f prime of 2 is equal to 0, f prime of 3 is equal to -1, f prime of 4 is equal to -2. Let's see what happens. If these are decreasing tangent slopes, let's draw it out. So this one would be equal to, whoa, I think I made a mistake. Nobody said anything, man. You guys asleep or awake or what? Just checking, you guys. There you go. Decreasing slopes from 1 to 0 to -1 to -2. That's decreasing. What happens to the tangent slopes? Well, if at 1 your slope is 1, then 0, you're part of the same curve, then -1, then -2. Oh my goodness, look what that tells you about the shape of the original graph. These all have to be tangent to it, so the original graph has to look something like this, which of course is concave down. Concave down, baby. I told you. This is an excellent test for concavity. Tells you that you can box this one. F double prime of C is less than 0. It means that F prime of X was decreasing. Where? Well, in some little tiny neighborhood around C at least. If you zoom in enough, you will find this decreasing there. And what does that mean? That means the slopes go down, down, down. That means the inclination goes. This is a slope going down for you. That's a slope going down. This is a slope going up. This is a slope going down. I told you. If F double prime is negative, then F prime is decreasing, and that tells you that F of X must be concave down. Down. See that? I told you. Pretty nice, huh? Very, very, very nice. What that means is that we're going to add some more stuff to our first derivative sketches. Remember before we used to have just these line skeletons, degree 1 skeletons? We can now add some curves to these. We can say, you know what? This one doesn't just go maybe straight, and maybe it goes like this. Add some curves to it, or maybe it goes like that. What is it going to depend on? Well, it would be that one if it was concave down, and that would be the case if F double prime of X is less than 0 near these points. I'll just pick some point C in the middle or somewhere around here. If F double prime of C is less than 0, it'd have to be concave down, so it'd be that. But it would be this one. If F double prime of C was greater than 0, it would have to come up, concave up. Beautiful test right here. Second derivative telling you something about the graph of the original function. It doesn't have to be increasing or decreasing. It has nothing to do with the first derivative. The function could be going down, which means that the first derivative was negative. This has nothing to do with the second derivative. The second derivative could still be positive or negative, which is another way of saying that you could go down this way or you could go down this way. And what would that depend on? Well, when would you have concavity down? That would happen exactly when F double prime of C is less than 0. And this one over here would happen exactly when F double prime of C is, of course, greater than 0. You'd have concave up. Told you. You see why they pay me? That's why they pay me. So, let me think. I think we've got all the key ideas here. We got all the key ideas. We just need to practice now. So here's the game plan. We're going to pull up some of the slides from last lecture where we had the degree 1 skeletons, and we're going to improve on them using exactly the same ideas with this new added concavity test. Capiche? Alright, let me pause this just for a second. Alright, this is going to start to make, well, it will make a lot more sense once we do an actual example. Don't worry, you're in good hands. So I pulled up a slide from last time. This is what we did last time. This was the degree 1 skeleton. We took its the first derivative. We found the critical points. Those are come in two flavors, where the derivative is 0 or where the derivative is discontinuous. Those are critical points. Because that's the only way that the first derivative can go from being positive to being negative. Either it goes through discontinuity or it goes through 0. And this is more or less what it looked like last time. And I cleaned it up a little bit for us today. I moved some of the stuff and slide this thing over. Now what I want to do, I want to go blue today. And I want to study the second derivative. For the second derivative, I completely ignore everything that happened last time. I don't care about the 0. I don't care about the 4. In fact, I'm going to erase those right now. That's how much I don't care about them. They have nothing to do with the first derivative. Okay, so for me, those are dead. Maybe I'll put them over here, 0 and 4. And maybe I'll patch up this one. My poor little line. So what I'm saying is I start with a linear. Right now there's only one region. The whole thing is one region. Now I go to work. I first look at the second derivative here. This was the first derivative, so then my second derivative, I go with blue just to distinguish today's lessons. Blue. F double prime of X, I'm looking here, and then I'm going to take the derivative. That would be 6x minus 12. That's my second derivative. I need to find critical points. I need to know where that's positive and where that's negative. Well, first let me find out where it's equal to 0. it's equal to 0 when x equals to 2. So that would be right around here, x equals 2. And it has no discontinuity, so that's a complete list of critical points. Just one critical point, which gives me just two regions, left of 2 and right of 2. Two regions. Okay? Now I'm going to check to see whether this is plus 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 or minus 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 or whatever. And I'm plugging things back into f double prime because I'm studying the sign of f double prime. So I pick something here like 0. Anything here. 1. Well, 1 would work. I take 1 and I plug it into here, f double prime, and check if x is equal to 1. I plug it into there. 6 times 1 minus 12. Well, 6 times 1 minus 12, that would be negative. So this is negative, 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 negative. That tells me something about the concavity for the entire graph from here leftwards until infinity. It tells me that the concavity is concave down. So from here to here it has to go down like this, and then from there to there it has to go down. That's concavity down for us right there. But wait, there's more. Let's check to the right of 2. To the right of 2 I plug things in here like say 5. That would give me positive. So it means that throughout this region over here the concavity is concave up. So from here to here, I told you there's two ways to go about it. There's this way or there's that way. Well, there's this way or there's that way. But the concavity is up, so it couldn't have been that way. It has to be this way. Again, there's two ways to go about it, this way or that way. But the concavity is up, so it has to go this way. Let me draw better. Concavity up again. Boom, it has to look like that. And that is a much, much better sketch of the graph because it includes concavity, includes the curves, rather than just a degree 1 skeleton. Incidentally, this point right here is famous. Whenever the concavity changes from either positive to negative or vice versa, these points are famous. They're called the inflection points. You may see them again in literature or other places. Inflection points. Anyways, that was fun. Again, let's try to go back to some of the slides that we had before and see if we can make improvements. At this point, we forget about these ones. These ones mean nothing to us. We already got all the information from them before. What we want to do today is we want to study the second derivative, the sign of the second derivative. So forget everything that happened last time. It's a brand new day here. F double prime is equal to, let me see, the derivative of 1 is 0. The derivative of that is negative 1 over x squared, so that becomes positive 3 over x squared. 3 over x squared, so that is equal to 0 never, no real number. However, it is discontinuous when x is equal to 0. So the only critical point here would be x equals 0. That would be over here, 0. The function is not even defined left of 0, so there's nothing to the left of it. So for all practical purposes, I've got one region and one region only, everything to the right of 0. It's either all positive or all negative. So we check something. Let's check, for example, I don't know, let's check. So now we've got to check the whole region. Either the whole thing works, the whole thing is positive, or the whole thing is negative. If the whole thing is, let me think. Alright. If the whole thing is negative, then it's all concave down. So maybe it has one of those cusps like this where it's concave down. If the whole thing is positive, it's concave up, so it curves nicely like this. How are we going to tell? Well, we've only got one region to check, so we pick anything on that region. And we pick, say, for example, I'll just pick 5. And that goes in here into the f double prime because we're trying to study the sign for f double prime. That would give you 3 over 25, and that's equal to positive. So this is positive, 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 and that's telling you something about the shape of the graph. It's telling you that it's concave up, just like this. And so there's two. Remember we talked about this before. There's two ways to get this, either this way or this way. You can go this way, down, or up. Concave down, concave up. Everything is concave up, so this goes like this. From here on, again, you can go concave up or concave down. But since it's positive, we're going with the concave up. And there you go. There's a nice improvement on our degree 1 sketch. This would be called the degree 2 sketch of the curve. I didn't use anything but common sense and some really nice ideas about the first and second derivative. Pretty nice. You guys want to try that one more time? Let's do that one more time. So again, I ignore these things. That's -1, 0, and 1. I'll just put them up there so I don't forget what they were. Let me see. That was -1, 0, and 1. All right, and then I go to work on my second derivative. Second derivative of x. So I take the first derivative. That would be -4 plus 12x squared, and I set that equal to 0. That would give you 12x squared is equal to 4. That would give you x squared is equal to 1/3. That would give you x equals plus or minus 1 over the square root of 3. That would be whatever. It's some number between, let me see, this is around 1/2. Let's go here, this way, and this one. So -1 square root of 3 and 1 over square root of 3. So I'm ignoring everything on the top, and now I have 3 regions to check. This region, that region, and that region. And to check them, I take numbers and I plug them into my second derivative. This is f double prime of x. By the way, there's no discontinuity, so there's no other critical points. I should mention that. We always check 2 things: discontinuities or equal to 0. So let's take something left of that, say like -1. If you plug that in there, -1 times -1 becomes +1, so that becomes positive. Let's take something like 0, that becomes negative. Something like 5, that becomes hugely positive. So there's my concavity. First it's concave up. Forget about the graph for now. Even before you look at the graph, this is concave up over here, and this is concave down, and this is concave up. You got it? Let's do it from here, all the way to the left is concave up. So here we go. There you go. Told you. From here to here, right here between my hands, is concave down. So it goes like this. Oh, beautiful. And then for the rest of it, is concave up. There you go. An inflection point there because you change concavities. Inflection point there because you change concavities. And a beautiful graph here. It's telling you the curve is going like this.